Hi everyone. I'm so sorry for not being at ETH. I obviously haven't arrived because of the coronavirus. So what I want to do is basically still give my talk, but just do it over Zoom. So what I want to talk about is basically why metatransactions in ETH 1.0 suck and what can we do about it. Now the context is that we've been building this service called any.sender for the past 6 months. And now we finally have some merchandise for the product as well. Now, the idea is that it's the first financially accountable API. What we've done is that we provide a very simple API for developers. They can send us up a meta transaction, we give it back a signed receipt, and in the signed receipt we'll say, we promise this meta transaction will be accepted by the blockchain by block 100. And then the developer can just sit back and it's up to us to guarantee that transaction gets in the blockchain. So we'll continually bump the fee until it gets in the blockchain by the deadline. So what's really cool, as a developer, you no longer need to deal with building your own transaction infrastructure, dealing with queues of transactions or bumping the fee. Our API will basically take care of that for you, and that's a win-win for both sides. We make a little bit of money, and the DApp developer saves on development costs, and they get to focus on their product. Now, what we use under the hood is something called a meta transaction. What I want to do for this talk is first talk about why transactions in Ethereum is a pain in the ass. What is a meta transaction? How could this be used? Then I'm going to talk about the any.sender service, and then I'm going to talk about one or two sticking points with meta transactions, and hopefully how we can make them much better in ETH 1.0 and in ETH 2.0. So let's just get started. Just move my little face here. So let's consider Ethereum transactions. We have the baby, and the baby wants to vote in the DAO. So obviously what the baby needs to do is create an Ethereum transaction. They'll sign the Ethereum transaction and they'll broadcast that to the network. And then eventually the miner will see the transaction and the miner can say, I want to pick that transaction out. I want to include it in my block and confirm that in the blockchain. And that's basically the life cycle of an Ethereum transaction. So that sounds really easy, doesn't it? So let's deep dive a little bit more into the Ethereum transaction itself. Now, one thing is that Bob the baby, Bob needs to have ETH in advance. If Bob wants to get this transaction in the blockchain, they have to pay a transaction fee, and this has to be in ETH. The second thing is that Bob has to pick a competitive fee. If Bob sends in a transaction with 1 Giwi, but the miner wants fees of 10 Giwi, then this transaction will never be picked up by a miner. It'll never entice a miner, and it won't get in the blockchain. And finally, Bob has to be careful of the replay protection. So every transaction has announced the guarantee this transaction cannot be broadcast to the network twice. And Ethereum has a really quirky rule that says the announce must increment by 1 for every new transaction. And that can cause some headaches, as we're going to see. So what problems arise when you're dealing with Ethereum transactions? Well, the first problem is, let's say we have 3 transactions. We have transaction 10, transaction 11, and transaction 20. Now, as I mentioned, the network rule on Ethereum is that transaction announce must always strictly increment by 1. So transaction 10 can get in, transaction 11 can get in, but what about transaction 20? Well, the announce just jumped by 9. So technically speaking, transaction 20 can never be accepted to the blockchain. It'll just remain in the pending pool, and in fact, it probably won't even propagate across the network. So if you're not careful as a user, you may send a transaction, and there's a guarantee that it will never get in. Problem number 2. What if Bob wants to send transactions out of order? So let's just say Bob wants to transfer a coin to Alice, Caroline, and Dave, or maybe Bob wants to process 3 different withdrawals. The order in which those transactions are processed, it doesn't really matter. All Bob cares about is that they eventually all get in. Now, if we want to send this out of order, the only way to do this in Ethereum is to have, in this case, 3 different signing keys, and each signing key is authorized to transfer the coins. And that's not always reasonable to ask of Bob to maintain n signing keys in order to support n concurrent transactions. Problem 3 is bad transaction fee management. So let's consider this very simple queue. We have transaction 10, transaction 11, and transaction 12. Now on the network, miners are only accepting transactions that pay a gas price of 10 Giwi or more. Well, if we look at transaction 10, 10 will only pay 5 Giwi. So that means the miner isn't going to pick up transaction 10, and transaction 10 is not going to get confirmed on the network. If transaction 10 doesn't get in, then this actually holds up transaction 11 and transaction 12 as well. Because remember, every transaction has to be accepted in order. So the only way to resolve this situation is to republish transaction 10 with a higher fee. Another issue that may arise is, what if the network gets congested, the pending pool is full, and then transactions start getting dropped from the network? Well, in this case, transaction 10 gets dropped from the network, and now transaction 11 and transaction 12 cannot be accepted into the network. Bob, the baby, has to republish transaction 10, hopefully with a higher fee, before transaction 11 and transaction 12 can be accepted. And finally, what if Bob has sent 100 transactions to the network and they're all pending? Then Bob has a new transaction that he needs to prioritize. Maybe there was a dip in the price and he needs to protect his CDP before it gets liquidated. Well, there's two ways to solve this. One, the easy solution is that Bob will send it from a new signing key. But of course, he might not always have a new signing key to send it from, or at least a signing key with funds. So the only other solution is that he has to reorganize the queue of transactions. He has to bump the fee of all the transactions and then pop the important transaction at the top of the queue. So that gets accepted by the network first, and then the remaining 100 transactions. And that's expensive, painful, and there's so many race conditions there that you never want to have to deal with that as a user. So this all sounds really annoying, but surely this is academic. Patty, you're an academic, you're just making, well, you're not making this up, but they're all theoretical attacks. Let's walk through this cute little story. So Taylor wrote this amazing Tweetstorm last week, and he basically highlighted the CryptoKitty story of January 2018. Now, the very first thing in her tweet is amazing. Problem number 4 arises. Transactions were getting dropped from the pool. If you have a queue of transactions and the first one gets dropped, none of the other transactions can get in until that one gets republished. So we've already seen this happen in practice. When there's network congestion, transactions get dropped, and that can stop your other transactions getting accepted. Now, as part of this story, Taylor and a few others were on this, I believe, Skype or Telegram chat, maybe that's more Skype, with some exchanges. And the exchanges are sending 5 transactions a second. Now, problem number 3 arises. The exchanges are sending thousands of transactions, but at the very start of the queue, there's a transaction with a really bad fee. And because it has a bad fee, it stops all the other transactions getting in the blockchain. So that's really frustrating. Problem 3 has now reared its head. So one really easy way to solve this that was recommended in the chat is to the exchanges. If you want to deal with this scenario really fast, send all of your transactions with a super high fee. Just so 250 Giwi is the gas price, and it will resolve all your problems. Now, when you look at the CryptoKitties, boom and congestion, the highest fee at the time was around 80 to 100 Giwi. So actually, these exchanges are going to have to pay over double the price to get their problem solved ASAP. And who really wants to pay 250 Giwi for a transaction? Well, in practice, this is such a big enough problem that Binance still pays 40 Giwi per transaction, and Huobi pays 35 Giwi per transaction, because they just don't want to deal with stuck transactions on the network, so they always overpay. Because today, you can send a 10 Giwi transaction, and you'll have the same confirmation time as a 40 Giwi transaction. But this is a much easier solution for them to deal with, and they're wealthy, I guess, they make enough profit, and they can deal with the high fees, or overpaying the fees. So back to the cryptocurrency story. So back in 2018, Nick Johnson came about, and he realized there was a bug in Go Ethereum. He submitted a patch, and he fixed the bug. And he told the exchanges, run this new version of Go Ethereum. It will estimate the fee really well, and it will solve your problem. Now there's 2 problems. 1, the exchanges are running parity and not Go Ethereum, so this doesn't really help. And 2, it's way too risky for them to swap from parity to Geth or Go Ethereum. As I mentioned here, all it takes is one 5-minute screw up to cause 12 to 24 hours worth of issues. And I have been where that is before. And for them, it's so risky to change their infrastructure on the fly, especially if they have thousands of pending stuck transactions. So, I mean, it's so unfortunate they were in that scenario. This is because they didn't have very good transaction infrastructure. Now, this is a source story, and the source story is still a better love story than Twilight, but there's so many more stories like this. In October last year, high network congestion on Ethereum causes DeFi issues. Some ICOs got delayed because of the CryptoKitty congestion in 2017. 100,000 transactions got stuck in the pending pool because Tether joined the network. We have these crazy gambling games like Fairwind that consume over 50% of all gas. This is also another interesting story with DeFi Saver. They're a very good team, but last year they had some transaction infrastructure issues. So their whole premise is that they get hired by customers to watch and protect their CDPs. If the CDP is vulnerable, they'll top up the funds and protect the CDP. The issue was that they sent out a queue of transactions, one had a low fee, all the transactions got stuck, and some of the CDPs got liquidated. So they had to refund their customers, because they're honest and they have integrity. They refunded their customers to cover the losses. But actually, one of the issues is that if your transaction can't get in the blockchain, you can lose money because of that. And that's so frustrating. And now the mother of all examples, like this is unbelievable, and it was sent to me over Twitter. This one dude tried to, send 1,700 ETH into an ICO. They paid a 400,000 Giwi. They paid $71,000 on a transaction fee. And it's a failed transaction. It failed. So they spent $71,000 on a bloody failed transaction. It's bloody mind-blowing. Like, that's just, I'm just speechless. I would love someone to spend that amount of money on the any.sender service. We'll make sure everybody gets in. Anyway, I hope this clearly highlights that dealing with transactions on Ethereum is painful AF. Can lead to a bad user experience, and in the worst case scenario, a loss of funds. And we believe, at any.sender, we believe metatransactions can make this so much better. So what is a metatransaction? The idea is that the user will authorize commands and not transactions. They'll sign a message that says, go to this contract, go to this function, execute this command. Now, historically speaking, they've always been associated with gasless transactions, which aren't actually gasless at all. The whole point is that someone else will pay the fee on your behalf. But I believe they're way more useful as a basic primitive than just gasless transactions. It's actually a very good, tool, or a tool in our engineer's toolbox to allow the customer to outsource the entire transaction infrastructure to a third party, in this case, any.sender. So what happens is that the baby will give a meta transaction to the postman, and the postman will guarantee that gets delivered to Ethereum. And all what really happens is that we get the Ethereum transaction, we pop the meta transaction in the payload, and then the real layer guarantees they keep bumping the fee until it gets in Ethereum. And that's exactly what we've built at any.sender. And in fact, as I mentioned, we are the first financially accountable API. Our service level agreement is literally the smart contract. So I'm going to briefly talk about how any.sender works before I go into some of the issues that surround meta transactions. So the first step, if you want to use any.sender, is that you need a balance. It's prepaid. So as a user, all you have to do is simply deposit ETH into our relay contract. And that's basically the registration process. In the future, I really want to be able to support Uniswap. So you could donate it, you could deposit an ERC20 token, we swap it in the ETH, and then we take an ETH deposit. But of course, that's going to be V2 because that takes a while. Now, the second part is when the user finally has some funds or balance on our service, all the user needs to do is sign a meta transaction and give it up to us. And in return, we're going to send the user a signed receipt. And in this receipt, it's pretty much going to say, this meta transaction will be delivered to the blockchain by deadline block 100. So we just guarantee that it will get delivered to the blockchain by this, this final deadline. And actually, as a keen observer, you'll notice our receipt says nothing about the gas price. Because the user no longer sets the gas price, they give us a transaction, and it's up to us to keep upping the fee until it gets in. So the user can sit back and let our API, the any.sender service, simply deliver that meta transaction. Now, what happens with any.sender? So any.sender will send the meta transaction to the network. That will go via our relay contract. The relay contract will make a log that we did our job, and then jump out and execute the command in the user's contract. Very straightforward. If it's a good service, then we're done. The relayer got paid, the user had their meta transaction delivered in a reasonable time period. They didn't have to worry about bumping the fee or dealing with queues of transactions. It's just a nice little API for most app developers. But what if any.sender provides a lousy service? We just don't deliver the transaction by the deadline that we promise. The user has a signed receipt with our promise. So the baby can submit this to the adjudicator contract. And the adjudicator contract will use a signed receipt. It'll look up the blockchain for the relay job. If it can't find the log, then obviously any.sender did not do its job or service. So there's two outcomes. Any.sender has to compensate the user based on a pre-agreed amount before a deadline, in a timely manner. And if the any.sender does not refund the customer, then eventually any.sender security deposit will be frozen, slashed, and will no longer be able to access it. And you can imagine the security deposit is like $10,000 or $20,000. So there's a real financial commitment that guarantee that any.sender will never provide a lousy service, because otherwise we're out of pocket because we have to compensate the user or we get slashed. And that's exactly why it's the first financially accountable API. It's basically a skin in the game service. It's non-custodial. So the user's pre-signing these meta transactions, these commands, and sending it to us, and we guarantee that gets in. We can't approve commands on behalf of the user. The whole point of any.sender is to deal with queue management. We'll deal with queues of transactions. We'll deal with thousands or hundreds of transactions. We'll order them, we'll bump them based on priority, and we'll continually keep bumping the fee as well until all the transactions get processed. And of course, there's this on-chain deposit, this skin in the game. There's a real financial commitment to say we will not deliver a lousy service. And I don't know of any other company in the world that gives you a strong guarantee that can be swiftly executed with a single transaction. That's why any.sender is really exciting. Now, some of our design goals has been, one, we want to be minimally intrusive. If you want to use the any.sender service, we don't really want the DApp developer to have to modify their contract, or at least to minimally modify it to support our service. We do not want to be intrusive in smart contracts. Two, we want to be environmentally friendly. We don't want to have a negative impact on the Ethereum network. We have to create a log for every job. We don't want to, bloat the state. So I won't talk about it during this talk, but we have something called the data registry, where we'll keep logs for, let's say, 60 days, and then we'll do one big batch delete and delete the logs. So actually, we're very careful not to bloat the Ethereum network. One really cool thing about any.sender is that we have this novel replay protection, and we can actually beat Ethereum. You can give us 10 meta transactions, we can deliver them out of order, and the replay protection still works. And I'll talk about that at the end. And finally, there should be a fair payment. If the relayer is going to send this job on behalf of the user, the relayer should never be at risk of not getting paid for the job. So now I've spoken about why Ethereum transactions are painful, why meta transactions are cool, and how any.sender uses meta transactions under the hood, such that anyone building on Ethereum can outsource their entire transaction infrastructure to any.sender. Now let's look into some of the gotchas. So meta transactions are used by several projects, not just any.sender. And this applies for every meta transaction integration, any meta transaction service, not just any.sender. So the fun begins. The biggest issue is msg.sender. What do I mean by that? Let's consider this really simple example, okay? There's a vote function, And it wants to verify that the voter has called this function before it runs through the election. Do you see the problem here? It's going to wait a second. Clearly, the problem is that the user gives us a metatransaction. We stick that in an Ethereum transaction, we sign it, and we broadcast that to the network. So the relayer, any.sender, is the msg.sender in this case. It's not the user who signed the command. So how do we get around this problem? And there's two ways to do it. So first, we'll look at the intrusive manner. What you could do is modify your vote function so it verifies user signature on the command, and then it'll check the signer's address and check if the signer was indeed a voter. Do you see another problem with this? There's no replay protection. So anyone could take this message, this metatransaction, and they could just keep resubmitting it to the network. And it will just keep getting processed and processed and processed. Now in this example, there's no real issue whatsoever. But if this is a transfer of financial transaction, maybe the user's processing 100 withdrawals, it would suck if that withdrawal message could keep getting reprocessed and processed and processed. So now what the user will have to do, the contract will need to verify the user's signature, then check the replay protection, and then check if this vote is registered for the election. And that's pretty damn intrusive, and that's something we want to avoid for anyone using metatransactions. And the really easy way to avoid it is that the user or the service can simply deploy a proxy contract. So the proxy contract deals with checking the user signature, checking the replay protection, and then it does a DOP call out to the DOP. And then the DOPS function is executed as normal using msg.sender. So this is minimally intrusive. It's not a new idea by us. Several people have built and proposed different ways to do proxy contracts. The issue is that it does incur a little bit extra gas, because now you have this account proxy, it has to do a DOP call, and there's some overhead for doing that. I mean, it's still very small, but maybe let's say for that it would be about 30K gas, because you have to store the replay protection, but it's not that much. So one question would be, well, what if we could have a get messy sender function? So in the DOP could say return msg.sender or grab the signer's address. So could we have both inside the contract? And we can. It was proposed by the GSN, and it's a little bit hacky, which is why I'm going to bring it up. So there's still a proxy contract, okay? So when the proxy contract does the DOP call to the DOP, it will again do the DOP call, it would forward over the command and the data. What it's also going to do is append an extra 20 bytes onto the end of the data, and that will be the signer's address. Remarkably, for whatever reason in the EVM, the DOP will not process those secret 20 bytes at the end of the data. It will simply just ignore that. Okay, so then what happens is that in the DOP, it'll run through the function, it will then go to msg.sender, and now it'll check, was this sent to us by the relay smart contract? Nope, return msg.sender. Yes, let's go fetch the signer's address. And this is important because now we've had to hard code in the relay contract's address into the DOP. And that's a little bit intrusive. And finally, we have this really funky assembly here, as you can see, because what's going to happen is that the contract will look at the data that was sent to it, go to the last 20 bytes, fetch the signer's address, and simply return that. And as you can see, this is such a hacky solution. So because it's so hacky, I've awarded it the Hackiness Award. So, congratulations to the person who wrote this code. I think it's actually really smart and clever and a really nice little trick using the EVM, but man, it's so bloody hacky. Now, the benefit of this approach is, one, in your DOP, none of the functions have to be aware of the signer field. It's always sent. It's sent when necessary and you fetch when necessary, but the DOP doesn't care about the signer's address at all. Two, now we're going to have a proxy contract that supports multiple signers. There could be Alice, Bob, Caroline, and Dave. They're all using the same proxy contract, and all the different addresses are sent over to the DOP. Now, the issue is that it's still quite intrusive into the DOP contract, and it implements a very specific relay standard, put in the signer at the end, using this crazy EVM tricks. Now, what is a little funky is that it's now available for every ERC20 standard. So if you want to use ERC20 and you're deploying a new ICO, you'll get this out of the box. So be aware that there is a really hacky solution in there. It's a cool hacky solution, but it's a little bit hacky. Now let's go into a real problem, okay? And a real interesting problem around metatransactions. Do you know how dot call works? Okay, so let's look at this very simple line of code. We're going to do a dot call. We say, when we call out to this contract to the DOP, allocate 3,980,000 gas to the DOP. So then the DOP can run through that, execution and then return true or false. Now, at this exact line of code, there's 4 million gas remaining. So my question to you is, how much gas is really sent to the DOP? How much gas is really going to be available when we get to the DOP and we start to execute? Will it be 3,980,000? No, it's not going to be that. Because dot call has a really, really funky feature. So when you do the dot call, it's always going to guarantee that at least 1/64th of the remaining gas is kept with the caller. So you can call out, you do your execution, you come back, and there's always some available gas remaining for the caller to finish the execution. So in practice, what's going to happen is that the dot call and the DOP is going to be missing 42,500 gas. It's expecting 3,980,000 gas. Is going to get 3,900,000, 37,500 gas. So I'm not really used to pronouncing millions anymore. But that's crazy. The impact here is that the relayer could actually, if they're smart enough of allocating the gas limit, they could collect the fee, execute out. It'll be a failed transaction. They'll come back and just complete. Now, I'm not too worried about any.sender doing this maliciously, but if you're not aware of the bug, it's really easy to trigger this in an accidental manner. And that means if it's accidental, the relayer is being honest, they're trying to execute your meta transaction, but the meta transaction is not sent enough gas. And because it's not sent enough gas, everything blows up. Remember, that's nearly like 50,000 gas is missing. That's a huge chunk and very easy that it could be accidentally triggered. Now, there's an EIP for this by Wigawag, running, and it's EIP 19300. So please look at that EIP. Please take it seriously. It's something that really needs to be fixed at the EVM level, and it's ridiculous that this is even a bug. I can understand the motivation now that I've looked into it, why they're doing it, but the consequences for relayers is very frustrating. Of course, we've deployed a contract fix for this in any.sender, and we're one of the first relayers to actually propose that fix, apart from Wigawag himself. Look at my happy smiley faces. I'm really happy we got that fixed before lunch. Cool. So one thing that's really annoying is that, and there's sort of a theme emerging here, the problem of msg.sender and meta transactions, it's a platform level issue that we're trying to fix at the contract level. Really, meta transactions should be a native primitive in ETH 1.0 and ETH 2.0. So one way we could fix this issue at the platform level is we introduce a new opcode or a new concept called the gas payer. So whoever pays the fee of the transaction is the gas payer, because it'd be gas.payer. As you can see here, let me move my face. You can see that, msg.sender, gas.payer. Okay. And then inside the transaction payload, we could actually have a list of meta transactions or commands, pre-authorized commands. It could have the signer, the contract, the command, and the replay protection here as well. And now what's really cool is that we could reuse the replay protection from the Ethereum contract, the contract model. We could reuse that replay protection for every signer and command issuer. So then we don't have to build replay protection at the contract level. It would also be really nice to open up the replay protection to some of our proposals like Bitflip, and I'm going to explain in a second. Now, one thing I should mention is that there have been some proposals around this idea. So there's one by Alex, one by Mika. Please go read those proposals. I think we could have, I think they could still be a bit more generic, where they could support a list of metatransactions or commands. But this should be a top priority for ETH 2.0, because if we have this built into the platform, it makes it really easy for Bob the baby to outsource all of their transaction infrastructure to any.sender or another relay service. And so then there could be very simple APIs that deals with interacting with Ethereum, and dApp developers can just focus on building their dApps and not infrastructure. One final contribution I want to talk about, because I think this is really cool, is that we can actually beat Ethereum's replay protection, and we can support out-of-order transactions. Okay, and we call this Bitflip. And the idea is that on the blockchain, there's a bitmap, 01001010000. And every time we send a new transaction, all we want to do is flip one bit in the on-chain bitmap. So here you can see in the off-chain bitmap that I'm going to send in 00000010000. So when this hits the blockchain, the bitmap I've sent in, one bit is flipped. On the on-chain bitmap, there could be countless different flips. All we do is an AND operation, a bitwise AND, and then we'll compute a new bitmap. We compare the new bitmap result with the off-chain bitmap. Now, if replay can be detected if the off-chain bitmap is equal to the result. Now, if the off-chain bitmap, for whatever reason, is different to the result, there's still one bit remaining, then we can actually execute the meta transaction. We can then flip the bit on the on-chain bitmap, and then we go our merry way. So that's cool. As the sender, now all I need to do is flip a bit, send, flip a bit, send, flip a bit, send. When that transaction gets accepted in the blockchain, it'll flip the on-chain bit. So if I try to send a transaction again, it'll go in, it'll verify that the bit's already flipped, and this transaction cannot be processed. So we have other contributions around this idea. This is really cool. We have Bitflip with ordering, so we can have, order transactions and on-order transactions. And then this idea called multi-nonce, where we can support up to n concurrent transactions at any time. So if you want to support 5 transactions a second, then we need, 5 different nonces, and we just do the ordering as normal. You can learn much more about that at the GitHub, PISA research/metatransaction comp. We've actually built the Bitflip one into any.sender. It'd be really cool to see other relayers use these replay protection, because it's just so much more flexible for the user, and hopefully someday they'll end up in Ethereum. So thank you very much for listening. At some point I'm going to write a blog that's a bit more detailed, and also more about our experience of building these, non-custodial relayers. But what I want to highlight to finish is 1, any.sender is non-custodial. We can only relay pre-approved commands. 2, the whole point of any.sender is to deal with queues of transactions. So you as a dApp developer or a wallet or an exchange, you don't have to rebuild that same infrastructure. And actually now you can benefit from better replay protection than what Ethereum offers, as I mentioned in the Bitflip example. And 3, our only job is to take a transaction, bump the fee until it gets in. So we make sure that you pay a fair price and you're not paying 250 Kiwi every time you want to relay a transaction. What I really want to highlight at the end of this talk is that the benefits of meta transactions, they way outweigh the problems that are associated with it, around msg.sender. And if we can make meta transactions a native primitive in ETH 1.0 and ETH 2.0, then actually all relayers will benefit, and all dApps will benefit, because they no longer have to build out this stupid infrastructure. They can just outsource it to a third-party provider. Now, what I do want to finally highlight, because I've got to shill any.sender because it's a really awesome service. If you guys do want to integrate with any.sender and you want to try out, using meta transactions to do that, Then one of the early benefits is that if you integrate with us today, you actually get a sanity check audit from us for free. In the sense that we want to make sure that when you integrate with a relayer, that your system is secure and there's no, subtle bugs. So we'll probably look at your contracts to make sure that it works as we expect. So you're actually getting, a free sanity check audit by integrating with any.sender. So again, thank you for listening. I hope I made the case that metatransactions are useful. There's some problems with them. We can make it a native primitive, and we should all come together to make sure that happens. Not just for any.sender, but for any third-party relay service. Cool. Oh, and one last thing. I bought this hat for ETH, but unfortunately I don't get to wear it now in person, so I'm going to do it now because we're all going to go to the moon. It's a little unicorn, so that's so Ethereum. Okay, bye guys.